So the last thing we're going to talk about here are something called dielectrics. Dielectrics are essentially things that you put in between the plates of your parallel plate capacitor. It doesn't have to be parallel plate capacitors, it could be any capacitor, but we're going to focus on a parallel plate one. So I'm going to draw, first of all, my parallel plates. Let's make you bigger. Okay, those should be evenly spaced. Just imagine for a moment that they are. And so now I've got these parallel plates. They're set up. It's lovely. And I'm going to put another material in between. And I'm going to make it as easy as possible for now. So when I have this, like so, I'm basically wedging some material inside there. Okay? And that material is going to be some non-conductor. Could be air. Air's dielectric constant, and you have no idea what that means yet, but hopefully you will, is essentially the same thing as a vacuum. So we're not going to worry about that too much. But it could be air. Could be a vacuum, which would just be a dielectric constant of 1. Or it could be something a little bit more interesting, like paper, or rubber, or a ceramic, or a plastic. So we can have any sort of material that's a non-conductor in there as a dielectric. If you put a conductor in there, you've defeated the whole point of a capacitor. You've turned the capacitor into a large wire. And that's it. So what's going to happen, though, is because the dielectric is non-conductor, the charge can't actually move from one place to the other place. But depending on what it actually is, it could polarize. And so sometimes you'll see solids in here, but sometimes you'll actually see things that are a little bit more liquidy, where they could, in fact, move around some, but they can't actually detach. You're not going to get just negative charges along this side and positive charges here. What you're going to get is you're going to get molecules, and let's just, you can imagine that I'm going to make it easy. There's like 2 molecules thick, okay? So what's going to happen is I'm going to end up getting some of these are going to become polarized towards their respective sides. Okay, the ones I'm not really drawing are not necessarily becoming strongly polarized one way or the other. They're kind of neutral still. But some of them are going to polarize. This is one way of modeling this or of looking at it. So some of these are going to polarize, and so I end up getting essentially a canceling out of some of the charge on the plate. So, for example, this positive charge is trying to create a field that goes like this. This one's trying to create a field like this. These ones, like that, like that, like that. But because I've got polarized molecules, they're trying to create a counter narrative. I've got a positive on this side, a negative on this side, and the positive and negative in between cancel each other out. So I end up getting a countering field. But it doesn't happen as strongly as it does with the plate, because this is not a conducting material. It's some sort of a non-conductor that's polarizing. Polarization is not ever going to match what the conducting plates of the capacitor can actually do. But the net effect of this is to reduce E for any Q stored on the plates. So if I have a charge plus Q on this plate and a charge of minus Q on this plate, and I've got a dielectric in here, I'm going to have a smaller electric field than what I had before. Now the consequence of that is that if E is smaller, V is smaller. Why is that important? Well, for any constant Q, if V is smaller, that means capacitance is bigger. So I can store more charge with less voltage. Now how does that work out here logically? The way that it works out logically, hopefully, is that I now have negative charges closer than they were before to my positive charge. Right? So think about that. I've got some negative charges that are now right next to the positive charges. Before they were all the way over here. Now they're right next to them. That makes these positive charges that are on the plate less repellent to other positive charges. I can store more positive charge on the plate. That allows me, when the moment comes and I want all these positive charges to flood out into, say, like a flash bulb or something like that, it allows me to have more charge here to come out. Okay, so it allows me to store more charge for the same amount of voltage. So this dielectric can be a pretty useful thing. How do we calculate the dielectric constant? So every material has a dielectric constant associated with it. That dielectric constant is going to depend on the material properties. How well does it polarize, for example. And the way that we're going to do that is I'm going to kind of simplify this a little bit. So I'm going to go into another page. I'm going to draw a new set of plates. Plate 1, plate 2, positive, 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 negative, negative, negative. And I've got a polarized material here, but it's fairly weak. Okay? So I'm setting this up, and if I look in a particular spot, and maybe this is not the best way to have drawn it, let's draw it like this. Negative, positive, negative, positive. So they're kind of sitting in between. I've done that for a reason, because it will make life easier for us. So I'm going to make a Gaussian surface. And my Gaussian surface is going to go like this. It does not go all the way through. It cannot go all the way through, because then I'd be enclosing zero charge. Right? If I continue this all the way over to here, I've got zero charge enclosed. But enclosing the surface that I have here, you can see that I have this whole side here is plus Q. I've got some negative charge that I'm enclosing. So my charge enclosed is less than it would be if the dielectric was not there. And what I'm going to do is I'm going to say that the charge density on the actual plate is plus sigma. And the charge on my dielectric on this edge is actually sigma prime. Okay? So my charge enclosed is going to look something like this. Sorry, my charge enclosed will be sigma minus sigma prime, because I'm subtracting out whatever charge density I have here. We're assuming that the charge densities that we're using are positive. I could very easily just be talking about that side as well. Times A. A being the area of my Gaussian surface, right? And the reason why I'm looking at that area is because that's the area of charge that I'm enclosing on the plate and the dielectric, so I can just factor that out. So now I can say that electric field times area, because remember there's no field coming out of this side, it's all going through this side here, right? So I've got field going like this. Okay? So I've got field going like that through that one area, so that's why I have E times A. And then this is going to be equal to the charge enclosed, which is sigma minus sigma prime times A over epsilon naught. The A's go away, which is very nice. And so I end up getting that my electric field strength is equal to sigma minus sigma prime divided by epsilon naught. Again, I have a smaller electric field than what I would expect given the amount of charge that I have stored on those plates, given the charge density there. So now we use a little bit of a trick, okay? And this is something that you might be wondering, like, why do we do it this way? The reason why we do it this way is because we know what the answer is, or at least I know what the answer is. Why the first people who came up with this did it this way, I don't know. It's probably an after-the-fact sort of thing. So they say, let sigma prime, the charge density on the dielectric, be equal to 1 over n times the charge density on the plate. Clearly, I think these two things are going to be related to each other. This will be some proportion of that, right? So depending on how good the material is at polarizing, this could be up to 1 times the charge density here, between 0 and 1. So this number here is going to be between 0 and 1. Why did we not just make sigma prime equals n times sigma? You'll see, I think, as we go through, okay? So, what we're going to do is we're going to say that, actually, if we go a step further, you're going to say that sigma is equal to, actually, let's go back a step. This is, I think, the way that the book does it. You can find this n factor, and that could be useful, I guess. What I prefer to do, though, is just actually go right for broke. So since I know the answer, I'm going to cheat all the way. I'm going to say that I've got sigma prime equals 1 minus 1 over kappa times sigma, where kappa is actually the dielectric constant. So kappa is, it's a terrible kappa, kappa is dielectric constant, okay? This is a case where things will hopefully make sense at the end. So if I have electric field, let me move over here a little bit. So if I have electric field equals sigma minus sigma prime, which I've said is now just simplified down to 1 minus 1 over kappa times sigma, and I divide that by epsilon naught. If I'm careful about this, in terms of distributing, I distribute my sigma here, and now I have sigma minus sigma plus sigma over kappa all over epsilon naught. Those sigmas just go away. So that hopefully explains my motivation for describing it in this way, that I can just get rid of a sigma. And that leaves me with, if I do a little bit of simplification, kappa times epsilon naught in my denominator. So my electric field, instead of being sigma over epsilon naught, it's sigma over kappa times epsilon naught. And so then, if I just follow this along to its logical conclusion briefly here, delta V being equal to the integral with respect to distance, and this is from like 0 to d, of sigma over kappa epsilon naught dr. Obviously, there's not going to be any real challenge to that integral. So we end up getting the opposite of sigma d over kappa epsilon naught, where sigma is equal to the total charge divided by the total area of the plate. And I'm going to substitute that in because capacitance is equal to Q over V. So I have Q over, substituting this in for sigma, gives me Q D over kappa epsilon naught A. The Q's cancel out, and I now have the capacitance equals kappa epsilon naught A over D. This is exactly the same formula that I had before for a parallel plate capacitor, except that now there is a kappa. There is, in fact, the dielectric constant. Kappa equals 1 for a vacuum. It's like 1.0003, I think, for air, so it's really small. Other things might have like 1.3, or they might have 7. There's really no limit on what that dielectric constant could be. But it's something between 1 and infinity, okay? And that's what our kappa then tells us. Kappa is the dielectric constant, and it's telling us essentially by what factor the dielectric increases the capacitance over replacement of a vacuum, okay? So all of that stuff that we did over here that looked weird, this in particular here, these two steps, that was all to get us to a very nice conclusion where we have a simple proportionality. Okay. Now, again, I don't know why the motivation was to do that initially, but seeing the conclusion, my guess is that they had a messy conclusion, and they were like, let's make the initial steps a little messier so that we get a nice clean conclusion. But that's what the dielectric constant does. It increases the capacitance by inserting a material that does polarization. Keep in mind that a vacuum has no particles and thus cannot polarize at all. And as a result, it offers no dielectric properties other than what you have in free space, meaning in a vacuum. So hopefully that makes sense for what a dielectric is and how it works, and you'll be able to use that wonderfully to your advantage in the homework.